Hello everyone, your pal 6Speed here, and today we are doing a lecture on basically the theory and operation of air conditioning systems. So we're going to go over the different parts of the system, how it works, the thermodynamics and theory behind it, and then at the end we're going to go over what some of our pressures in the system mean versus what kind of problems you may have in your AC system. It's just going to be a general overview. We're not going to go into too much specific information, but this is just kind of meant to be more of a theory and operation type of thing. So, air conditioning, how does it work? So, air conditioning works by using the refrigeration cycle. Basically how your fridge works, your freezer works, your household air conditioner works, even your heat pump if you have one in the house, all work the same way as your car air conditioner. Just your temperatures may vary. The difference with the heat pump, though, is that the heat pump can actually reverse. It can go in both directions to produce hot air and cold air. So we have our 4 different stages of the cycle, starting with compression, condensation, throttling, and evaporation. Now we're going to go into this a little bit further later on in the lecture. So before we get started, we need to note a few key points that will make visualizing and understanding how this system works easier. So heat is thermal energy. So the hotter the air is, the more thermal energy it contains. You're not actually cooling the air per se, but you are actually removing the thermal energy from it. Energy is not created nor destroyed, but it is transferred from one place or state to another. Pressure plays a very critical role in refrigeration. A liquid will boil at a low temperature under a low pressure, or even a vacuum. We'll get into that a little bit later too. On the other side, a liquid will actually boil at a higher temperature under a higher pressure. This is known as the vapor pressure. The heat of vaporization is the amount of heat required to boil a liquid. As the boiling point changes, so does the heat of vaporization. Temperatures and pressures will always want to return to an equal state. This is known as an equilibrium. As a result, pressure will flow from an area of high pressure to an area of low pressure in order to achieve the equilibrium. That's how we maintain refrigerant flow in the system. Also, it's the same thing with temperature. It will also try to form an equilibrium. It will come to an equal state where thermal energy will tend to flow from an area of high energy to an area of low energy, and this creates a balance. This is how an air conditioning system works, is basically just transferring the heat from an area of low temperature to a high temperature and vice versa. So let's go over the refrigeration cycle. So this is a basic lousy drawing of mine overview of how a refrigeration system looks. This is coming from an automotive air conditioning system. So we have our compressor. It's driven by the engine, usually by a belt. So the line leading out of the compressor into the condenser is known as the discharge line, or the high side pressure line. So our condenser removes the heat from the refrigerant and allows the refrigerant to condense into a liquid. So we have our radiator fan, or even just the motion of the vehicle that blows air across the condenser fins, the refrigerant being hot and the ambient air being cooler than the refrigerant. As the cooler air passes over the condenser, it transfers the thermal energy from the refrigerant through the aluminum fins in the condenser into the air. That's why when you put your hand kind of near it, when it's running, you can feel the heat coming out of the radiator fan, not only because of the radiator, but because of the condenser as well. So we have our throttling device. This can be an expansion valve or an orifice tube. We will go a little bit more in depth into this a little later on. And so after we pass our throttling device, we are now on the low side of the system. So on the low side, we have the evaporator, which is contained inside your HVAC box. The blower fan will blow air across the evaporator, which is warmer than the refrigerant within the evaporator. And same thing with the condenser, but in the other way around. It transfers the heat of the air, the thermal energy, into the refrigerant, and as a result, you get cold air coming out into your cabin and you're nice and comfortable. And so the line leading from the evaporator to the compressor is known as the suction line. So compression. The compressor sucks a hot gaseous refrigerant from the evaporator and pumps it into the condenser. Anything before the compressor but after the throttling device is known as the low side or the suction side. Anything after the compressor but before the throttling device is known as the high side or the pressure side, sometimes called the discharge side. So condensing. After the refrigerant is sent into the condenser, it expels its heat out into the ambient air. When the refrigerant cools, it condenses into a liquid, hence the term condenser. The refrigerant remains a liquid because it's under a very high pressure, which prevents the liquid from boiling. So our throttling device is used to force the liquid refrigerant through a small opening. This results in a substantial pressure drop between the two sides of the throttling device. The refrigerant basically becomes an atomized liquid or a mist under low pressure. You know, you ever take your hose and put it on mist and it's nice and cool when you walk through? So a liquid under a low pressure boils very easily. So now we go on to our evaporator. So as the warm air is blown across the evaporator coils, the heat gets transferred from the air, the thermal energy is transferred from the air into the refrigerant. As a result, the refrigerant actually boils into a gas. Even though it's atomized, it's not quite a gas yet. So once it picks up the energy, it then vaporizes into a gas. And the hot refrigerant is then sent back into the compressor in order to continue the cycle. So now we're going to talk about pressures, and there's two different types of pressures when we measure them. We have absolute pressure and we have gauge pressure. Absolute pressure takes the atmospheric pressure into account. In an empty tank that is exposed to the atmosphere, an absolute pressure gauge would read approximately 14.7 psi, or absolute. Gauge pressure does not take into account atmospheric pressure. So that same empty tank would have 0 psi gauge. An air conditioning system is generally, I haven't really seen it ever, but you never know, measured in gauge pressure, as most things usually are. So the effective pressure on a boiling point of a liquid. So for this example, we're actually going to work in absolute pressure because it's easier to understand in this sense. So atmospheric pressure of 101.325 kilopascals, also known as 14.7 psi, water boils at 100 degrees Celsius or 212 degrees Fahrenheit. If you put that bowl of water in a chamber and put it under a vacuum, so we'll drop our absolute pressure down to 2.34 kPa or about 0.34 psi, so we're almost in a perfect vacuum. The water actually boils at 20 degrees Celsius, so that's 5 times less than what it was before, or 68 Fahrenheit. So now we'll talk about our refrigerant in our system, and we will actually be working gauge pressure since every example from this point on will actually be in gauge pressure. At atmospheric pressure, so 0 psi gauge, R134A, which is a very common refrigerant used in just about every vehicle today, boils at minus 14.92 degrees Fahrenheit or negative 26.1 degrees Celsius. So R134A is actually a gas at room temperature at atmospheric pressure. The typical static pressure of an AC system at 70 degrees Fahrenheit or 21 degrees Celsius is around 70 psi gauge. So the boiling point at 70 psi is 69.24 degrees Celsius or 20.7 Celsius. Celsius. Sorry, my mistake. R134A is a gas at ambient temperature when the AC system is properly charged. When the compressor is engaged, it pulls the refrigerant from the low side, causing the pressure on the low side to drop from the static pressure. The compressor pushes refrigerant into the high side, which increases the pressure over the static pressure. Static pressure is basically what you have when the compressor is not running. So our typical low side pressure when the system is operating at 70 Fahrenheit or 21 Celsius is about 35 to 40 psi. which means that the refrigerant is definitely going to be a gas on the low side of the system, if the refrigerant is usually a gas at a static pressure. So one thing you have to remember with this is as the temperature changes, so will your high and low side pressures and your static pressure, because as the system heats up, refrigerant is going to want to expand. Since the system is closed and sealed, the pressure will go up. So that's why I'm giving you the ambient temperature in these examples. So R134A, the boiling point at 35 psi is 39.9 degrees Fahrenheit or 4.4 degrees Celsius. So typical high side pressure under operation at 70 Fahrenheit, 21 Celsius, is about 145 to 160 psi. R134A is a liquid on the high side after the condenser. The boiling point of R134A at 160 psi is 115.6 Fahrenheit or 46.4 degrees Celsius. The low boiling point at low pressure allows the refrigerant to absorb the thermal energy as it boils. This removes the thermal energy from the air. The high boiling point of the refrigeration on the high side of the system allows the refrigerant to expel the thermal energy as it condenses. So it expels the heat from the refrigerant into the ambient air. So why do we want the refrigerant to boil in the evaporator? Well, liquids are virtually incompressible, so we do not want to send liquid refrigerant into our compressor. So in order to pump the refrigerant under pressure, it must be a gas, because if a bunch of liquid refrigerant went into the compressor, it would hydrolock and damage the compressor. So the change of state from liquid to gas actually absorbs the heat from the surrounding area. So why do we want our refrigerant to condense? Well, the change of state from gas to liquid helps expel the heat that it absorbed into the atmosphere. When throttled through an orifice or metering valve, the liquid refrigerant actually becomes misted or atomized, much like a carburetor atomizes fuel into the intake. That'll be another lecture for another day, carburetors. The atomized droplets of refrigerant have a lot more surface area, which allows the refrigerant to boil and absorb heat a lot quicker. So now we're going to talk about the components of the system. We have our AC compressor. So we have our compressor clutch on the front. So this is so that the compressor doesn't get driven constantly by the engine. That would kill your fuel economy, and it would cause a lot of unnecessary wear and tear on the compressor. So when you need the AC, the clutch will engage, spin the compressor. Otherwise, that pulley just freewheels all the time on the compressor shaft. We have our drive pulley, which is driven by the belt from the engine. So we have our low side inlet suction port, and we have our high side outlet discharge port. So this is basically a cutaway view that I've drawn. So we have our drive pulley. This is called a swash plate, and what the swash plate does is that allows the compressor pistons to ride on it, and so as the casing of the internal casing, the piston casing spins, it allows the pistons to move up and down. So we have our outer casing, we have our carrier, and the piston. So as the carrier rotates, as you can see by the blue arrow on the right-hand side there, the pistons actually move up and down in their bores, compressing the refrigerant. So the inlet side is the low pressure, the vapor side. That's when the pistons come down, it draws it in from the low side. As the pistons go up, it pushes it out, the discharge side. So the compressor is the heart of the air conditioning system. It pumps the refrigerant vapor from the evaporator into the condenser. Now it's lubricated by an oil carried by the refrigerant. It's known as PAG 46. That's what the vast majority of air conditioning system uses. A lot of hybrid vehicles will use something different. But basically, the refrigerant almost dissolves within the the oil dissolves within the refrigerant, and that's what lubricates the compressor as the refrigerant goes through the system. Without it, the compressor would seize up very, very quickly. So our electromagnetic clutch drives the compressor. When power is applied to that clutch, it engages with the pulley and spins the compressor. So the clutch prevents the compressor from being driven when it's not necessary, again, for fuel economy and for wear and tear. So the low side actually has a pressure switch, which prevents the clutch from engaging if the pressure falls too low. Usually about 20 to 25 psi or so, I've heard, or maybe even down to 10. I've heard a bunch of different points where the low pressure switch will cut the power to the compressor clutch. So basically, it prevents the compressor from seizing up from lack of lubrication if the charge becomes low or empty. We have our condenser. So our condenser condenses a high-pressure refrigerant vapor into a liquid by expelling the heat from the refrigerant into the atmosphere. As the air is blown across the condenser fins by the motion of the vehicle or the radiator fan. At a slow or stationary speed, the radiator fan does most of the air moving across the condenser. So our orifice tube basically is one of our throttling devices. There's two different types. We have our orifice tube and we have an expansion valve. This one is the simplest of the throttling devices because it doesn't really do much of anything. It's kind of just a fixed metered orifice. So our orifice tube is placed in the AC line after the condenser and before the evaporator core. So there are two main types. There's fixed and there's variable. I haven't seen too many variable ones. Apparently they are not particularly reliable, I've heard. So the fixed orifice tube has a single outlet size that does not change. So a variable orifice tube uses a bimetal spring to block off an additional port that will open up at higher speeds and allows more refrigerant flow. So since it's fixed, it provides zero pressure regulation at all. It's just a restriction in the system. In order to regulate the pressures, the compressor is actually cycled on and off while you drive. Sometimes you'll hear the vehicle, you can hear the compressor click in, and it'll kick on for maybe 5 to 10 seconds, then it'll kick off. If the compressor isn't cycled, the high side pressure can become excessive and the low side pressure will fall too low. And this will actually result in the evaporator core icing up from the moisture freezing inside the housing. So our other system is called a TXV, or a thermal expansion valve. Basically, it uses a pressure diaphragm with a capillary tube, and the capillary tube, the remote bulb you can see at the bottom there, sits on the evaporator. So as the temperature changes, the expansion valve can move to let more or less refrigerant through accordingly. So it meters the refrigerant flow into the evaporator, and it kind of regulates the flow. The metering is controlled by the temperature inside the evaporator core. The bulb pressure counteracts the superheat spring, changing the flow of refrigerant through the TXV. As the valve closes, the pressure on the liquid refrigerant drops as the mass flow rate of the system drops. The job of the TXV is actually to regulate the flow of refrigerant through the system. It is not to regulate pressure. What it does is it maximizes the system efficiency and prevents the liquid refrigerant from entering the evaporator. If a liquid enters the evaporator, it could quote-unquote slug the compressor with a shot of liquid, and that would damage the compressor very quickly. So now our last piece of the puzzle, we have our evaporator core. So it basically works like the reverse of the condenser. Air gets blown over the evaporator core by the blower fan, and the hot air being blown across the evaporator causes the refrigerant to boil. This helps remove the heat from the air. So there's two other components. Well, I guess there's one other component to the system. It just depends on which you have. In this case, there's a receiver dryer, which is kind of important. So the receiver dryer is used in a TXV system. And what it is, well, we'll get onto it. It serves a very, very important function. So it's only used in a TXV system, and it contains a desiccant that absorbs any kind of moisture that may have entered the refrigerant, say if the system wasn't vacuumed down properly. So moisture freezes and ice crystals can actually plug up components and cause damage to the compressor. So if the system has gone completely empty, if the system had a leak in it, and what ends up happening is if the leak isn't fixed, the system is now exposed to outside air, and as the outside air rushes in, it can saturate the desiccant. So because our outside air contains humidity, the desiccant will absorb the moisture out of the air and become saturated. So if the system is open to atmosphere for any extended length of time, you have to replace the receiver dryer. I've seen people try to bring them back by vacuuming the system for a long period of time. Best thing to do is just to replace it. So in a TXV system, it is located on the high side of the system after the condenser and before the TXV and evaporator core. So this holds the refrigerant and oil during times of low cooling demand, and it contains a filter to trap debris. Usually debris happens when the compressor kind of explodes internally. It'll send shrapnel through the system. So on the other side, we have an accumulator. This is used in a orifice tube system. So only used in a system with an orifice tube. It's about twice the size of a receiver dryer. And it's connected on the other side of the system to the outlet of the evaporator before the compressor. And what this does is this uses, it's able to store the liquid refrigerant after the evaporator, which prevents slugging the compressor with liquid. It also stores refrigerant and oil and has desiccant like a receiver dryer. So this is our system layout with an orifice tube. You can see that our accumulator sits between our compressor and our evaporator. And our TXV system, the receiver dryer sits on the high side after our condenser before our TXV. So now we're going to talk about our effective humidity. So humidity in the air plays a very critical role when using this style of air conditioning, refrigeration style. Because basically the way that this works is you dehumidify the air by cooling it. So air conditioning works by the system of dehumidification by cooling. The higher the air temperature, the more volume of moisture the air can hold. Like if you have hot water, you can put more sugar in it and dissolve it than you can with cold water. Same kind of thing. Air is basically moisture is dissolved within the air. This is called water vapor. So the ratio of moisture in the air compared to complete saturation is known as relative humidity. 100% relative humidity means that the air cannot hold any more water vapor. It is completely saturated. 0% relative humidity means that there is no water vapor present in the air. So as our temperature decreases, the maximum amount of water vapor that the air can hold on to decreases. The amount of water vapor in the air actually does not change until the air is cooled to the point where 100% humidity is reached. So this means that as we cool the air, the relative humidity will increase until it hits 100%. So at this point, the air cannot hold any more moisture, so what ends up happening is the moisture will actually precipitate out of the air. So it collects all over the evaporator housing, and what ends up happening is it ends up draining down a tube in the bottom of the evaporator. And so you ever seen a vehicle parked out on the road or something like that on a hot day that's had its AC running, you can see it dripping water out of the bottom. That's because of the dehumidification effect. So in order to prevent the air from entering the cabin at 100% humidity, we warm it ever so slightly with a very small amount of warm air. And what this does is it causes the humidity, relative humidity, to drop because a little bit warmer air can actually hold more moisture. So since warmer air can hold more moisture, as we warm the air, our relative humidity now drops. So if the air entered the cabin at 100% humidity, the air would feel very kind of clammy and sticky and gross. So if the compressor is the heart of the system, the blood of the system is the refrigerant. So we have a few different automotive refrigerants that are used. What we call CFC R12, also known by its trade name of Freon by the DuPont company. Freon is generally a term that's thrown around, but that is actually only a trade name from DuPont. We have HFC R134A, which is extremely common. It's still used today. We have HFO R1234YF. That's a bit of a mouthful. This one has come into play a little bit more recently, as has HFC R152A and R744, which is basically pure CO2. So we have other refrigerants such as R22, R32, R410A, R407C, and R600A, just to name a few. Those are not generally used in automotive applications, but stuff like building AC and household AC units, other refrigeration systems like refrigerated trailers, stuff like that. So, R12. Again, trade name is known as Freon by the DuPont company, and it has been completely phased out by 1995 model year, and it has been replaced with 134A. So since it's a CFC, which stands for chlorofluorocarbon, it causes extensive damage to the ozone layer, and it is a very, very potent greenhouse gas. So an R12 system uses a mineral oil to lubricate the compressor, much like basically like a conventional motor oil type of thing, so a non-synthetic. You can convert an R12 system to R134A, but it does require draining the oil and replacing it with PAG 46. You also need to change the service port valves because the service ports are different between an R12 and a 134A. So manufacturing of R12 has long since been illegal because it's very dangerous for the environment. You can still buy it kind of new old stock, but you actually technically need a special license to buy and sell it. So you can replace it with a refrigerant called R12A, which is actually a mixture of propane and butane. R12A can be illegal for sale in some areas because some areas do not permit a flammable gas to be used as a refrigerant. And it is also illegal to recharge or top up a system with R12A unless you fully evacuate the old refrigerant. Also known as, well, you can do this for both R12 and 134A. It can be used for both. And again, if you're charging with R12A, you have to replace the fittings to an R134A style. So R134A, again, extremely common refrigerant nowadays. It's still even used in new cars today. So it replaced R12 after 1995 model year. And we use our synthetic PAG 46 oils. Again, some hybrid vehicles use something a little bit different. It's what they call an HFC, or a hydrofluorocarbon, so it's actually harmless to the ozone layer. But it is a very potent greenhouse gas, but not as near as bad as R12. It is, like I said, it's still commonly used today. Now, new regulations have caused it to be phased out by 2021 in new vehicles. But the only difference is, unlike R12, is R134A vehicles will still be allowed to be serviced. This may change in the future, but as of right now, any vehicles running R134A do not have to convert to something different just yet. So our R1234YF is a slightly horse of a slightly different color here. So it kind of been approved for automotive use in around 2012, around 2014, I think is when a few of them started appearing. It's been adopted by Fiat Chrysler, some GM models, a lot of Cadillac, stuff like that, Tesla and Land Rover in certain models. It is mildly flammable, unlike R12 and 134A. And this actually requires a high-pressure cutoff switch, a pressure relief valve, and special fittings so that you cannot charge it with the wrong stuff, and if there's an issue, it can vent. This also requires an inline heat exchanger. It's slightly different from a normal system. This stuff is very expensive and kind of makes it infeasible to convert an old R134A system to 1234YF. The inline heat exchanger has liquid refrigerant from the condenser flowing through the inside of the heat exchanger and the gaseous refrigerant flowing from through the outside. So it's built into the accumulator on an Orifice tube system, and it's actually built into the pressure hose after the condenser before the TXV on a TXV system. So the still cold low pressure gaseous refrigerant supercools the high side refrigerant to far below condensation temperature. So R152A is also mildly flammable like R1234YF, and you are required by the EPA to have a strategy to detect any foreseeable leaks in the cabin. And if there's an issue, there has to be a strategy to prevent any buildup of refrigerant. It has been used by DIYs in place of R134A with decent results, but it's currently not approved for a retrofit of R134A systems. R152A has a much lower greenhouse gas effect compared to 134A. And finally, our R744. This is actually used by Mercedes and BMW because of the flammability issues with R1234YF. Pure CO2 is actually used as a refrigerant, but the EPA requires an engineered method that avoids a buildup of carbon dioxide in the passenger compartment in the event that the evaporator decides to leak. This is so you don't die of asphyxiation inside the car. So pressures being about 4 times that of an R134A system makes retrofitting to R744 expensive and very unlikely. So we have 2 other things that are mainly added to our refrigeration systems when we're talking about refrigerants. We have UV leak dye, which actually can come in a pressurized can. You can actually put a dye shot into the AC system yourself. With caution, of course. A lot of places you can't buy AC stuff without a special license. But this is the best way of detecting a leak. We'll go into that a little bit more later. And we have sealants. I have questions on whether they work particularly well. It's kind of a Band-Aid fix in my opinion. If there's a leak, you should fix it properly. So now we're going to get into service of the system. So refrigerant recovery is kind of our first step. So releasing the refrigerant in the system into the atmosphere is called discharging. And discharging into the atmosphere is very illegal. So recovery is when a special machine is used that sucks the remaining refrigerant out of the system and stores it in a tank. So recovery is done before the system is serviced. You can't really service the system while it's under pressure. Manifold gauge set is the quintessential tool for AC work. Even if you have a fancy machine, manifold gauge set is built right into the machine. So you cannot service the AC system without it. So the knobs on the manifold allow the specific port to be open to the center hose. So if you open up one of the ports with pressure in the system without anything on the center hose, refrigerant will just pour out the center hose. So if you connect the fitting to the AC port and open the knob on the fitting, then we open our system up to the gauges, and the gauges will read the pressures at their specific ports. So evacuation. So after we service or repair the system and it's complete, we have to evacuate the system. So if the system was opened by removing a hose and the inside of the system is exposed to the atmosphere, any air and humidity at all that enter the system has to be removed. If we have air in the system or any kind of humidity, it ain't going to work properly. So we put a vacuum pump and we attach it to our manifold gauge set on that center hose, and we open up both of our high and low side port and fire up the vacuum pump to suck all of the air out. So just because the air was removed from the system doesn't mean that the moisture was. So what we need to do is we need to hold that vacuum on the system for 30 to 60 minutes. So again, remember how we talked about the effect of pressure on boiling point. So if we hold the system in almost a perfect vacuum, it'll boil the moisture off at ambient temperature and it'll completely clear our system out. The vapor is expelled from the discharge of the vacuum pump. So as we're evacuating the system, we do not turn the vacuum pump off and we do not close our manifold gauge set. So it's always sucking down on the system. So we need to check our system for leaks before we actually go too much further. So when we place our vacuum on the system and we open up our manifold gauge set to place the vacuum on the system and we shut them again, it should hold vacuum on the system. So when we shut our vacuum pump off, because the vacuum pump won't be doing much of anything, our gauges should stay at a vacuum. So we seal our system off with a vacuum in it. And so our vacuum should hold steady for 15 to 30 minutes. And if it does, we consider our system to be sealed. And we can evacuate the system to boil off any moisture. If it doesn't hold, if it returns back to zero, then or starts creeping up, then we know that our system has a leak. So in a charged system, it's very hard to find a leak by visual inspection because usually leaks are tiny. Since the AC leaks are very, very slow detection methods, other detection methods need to be used. So there's two ways. We have a refrigerant detector with a little sniffer end on the thing, and the thing will actually beep when refrigerant's detected. So our refrigerant detector kind of looks like this. Kind of a simple tool. Got that little schnoz on the thing to detect the refrigerant. So it's kind of hard to pinpoint leaks with this thing, especially under the hood. So the sniffer is actually best for checking for leaks inside the evaporator core because you can shove it down in the vents, and if the refrigerant is leaking, it'll beep. It's really hard to see the evaporator without taking half the car apart. So you kind of want to confirm this, and you can't really see it with your UV light, which is the other method. So UV dye is the best method for leak detection under the hood. Sometimes you can actually see it coming out of the evaporator drain. If it's bad enough, you can see the dye in the drain hose. So you basically put your orange glasses on and use a UV light, kind of like the dudes in CSI, and the dye will glow like a nice luminescent green, kind of yellowish color when the UV light hits it. So common leak points. The most common leak point is the service port Schrader valves. A lot of people overlook this, and it's hard to detect because if you add any dye to the system, there's obviously going to be dye at the service ports. Sometimes you put your ear right up close to it, you could kind of hear it gurgling. Compressor shaft seal is the second most common point of leak. This will slowly weep refrigerant over time. So after about 5 or 6 years, you may just have to have the system recovered and recharged because of it. O-ring seals between hose connections, and sometimes a condenser from damage from debris or an accident. They don't typically start leaking on their own, but they do sometimes. And the evaporator core, again, some kind of corrosion get in there, maybe cause a leak at the evaporator core. And so hoses, we can have abrasion damage, burst or torn, something like that. Had that happen before. So recharging the system. So after evacuation, it's time to recharge. So we always refill our refrigerant by weight using a digital scale to weigh the tank during the charging process. So since the refrigerant changes state quickly, it's very difficult to measure the volume when charging. That's why we charge it by weight. Charging is always done through the low side. We never, ever charge on the high side. The refrigerant mass can generally be found on a sticker underneath the hood, sometimes in service manuals, sometimes in owner's manuals. Don't ever add any extra refrigerant because overcharging the system will damage the compressor, and it has the same effects as undercharging the system. You won't get as cold of air. So when starting the recharging, the refrigerant will slowly enter the system just by the pressure in the tank, pushing the refrigerant into the system because the low side pressure switch hasn't been tripped yet to start the compressor up. So at a certain point, when the pressure on the system becomes high enough to trip the low side pressure switch, it kicks the compressor on. So what this will do is it'll quickly pull the refrigerant from the system. So you always have to pay close attention to the scale during charging. And you always want to charge the system very slowly because if the service port is very close to the compressor, you could easily slug the compressor with liquid. So don't want to do that. You can damage it very easily. So we're going to talk about pressure readings and common problems. So learning how to read your manifold gauges is a very key point in diagnosing a system effectively. So every case is different. So I'm just going to kind of give a general overview of what the pressure readings are. So the readings I am giving are ideal and based on a constant ambient temperature. As your ambient temperature changes, both your static and your dynamic pressure readings are going to change. So yeah, don't forget this. This is very, very important. Again, general case. So AC work takes experience and training. So the info I'm giving is just general. So static pressure is the system pressure when the compressor is not operating. So when you connect your manifold gauge set, your low and your high side should be equal. If they're not, you could have a blockage somewhere in the system, or your manifold gauge set might not be functioning correctly. So if the static pressure is around what it should be for the ambient temperature, we cannot trust that as God to say that the system charges good. If the static pressure is a lot lower than what it should be, then we can be safe to assume that the system charge is low. So we're going to go from approximately 70 degrees Fahrenheit for our static pressures with Now the gauges I've shown in this picture are actually meant for building air conditioning, stuff like that. You can see if you look very closely, it does have R12 on there even. So the temperature it corresponds to on the low side is actually the evaporator temperature, and on the high side is actually the condenser core temperature. That's a little bit more for household refrigeration, but it can help you pinpoint issues if need be. But if you're doing R134A, you need to have a gauge that reads for 134A. This will still read the pressures, but your condenser and evaporator core temperatures are not going to be correct. So with R134A, generally your static pressure is very, very close to what the ambient temperature is in Fahrenheit. So if we're going from 70 psi, both gauges should read approximately 70 psi. So ignore the black needles and just look at the ones I've drawn on there. I know it's kind of cheesy. So if our system's low, again, 70-degree ambient temperature, you're going to see the gauges are quite a bit below what it should be. So we know that our system charge is low, so we got to start by looking for a leak. So if the charge is high enough to trip the low side pressure switch, the compressor will cycle on and off very quickly. So it'll click on, then click off, then on and then off, and then on and then off. Because what's happening is when the low side pressure drops below the pressure threshold of the pressure switch, it kicks the compressor off until it comes back on again, until it comes up enough for it to kick the compressor back on. So like I said, it quickly falls below the minimum, and then it'll kick the compressor off until it builds back up enough. If the charge is extremely low, it may not even kick on at all. So our normal AC operation, again, this is general. So we see our high side pressure has come up over ambient, and our low side pressure has come down over our static pressures. So if both our high side and our low side are abnormally low, then we can assume that our system is most likely undercharged, or there's too much oil in the system. If somebody's replaced a compressor, sometimes the compressors come full of oil, and that like doubles the oil in the system. It's all dependent. So yeah, don't add extra oil unless you have to, kind of thing. You know, it's all case dependent. So in a variable displacement compressor system, which has basically a way of kind of increasing the volume output of the compressor to kind of increase engine drive efficiency, we could have an expansion valve failure, or we could have a blockage between the dryer and the evaporator. So if our high side is high and our low side is high, then our causes of our condition is it's likely that the system is overcharged. Somebody's added a can of refrigerant just willy-nilly and not realize they put too much in. We could also have a blockage at or before the TXV or orifice tube, or we could have poor airflow through the condenser, like plugged fins type of thing, so we can't transfer the heat out of the high side. And another cause of this, we could have moisture or air in the system. For a variable displacement compressor system, we could have a failing control valve, the valve that controls how much output the compressor delivers. So we got a very, very low side and a very high side. Then common causes for this are usually a blockage in the orifice tube or TXV can cause this. Our evaporator could be frosted, usually from lack of airflow. We have air in our system, so if somebody didn't vacuum out the air before charging it. Our expansion valve stuck closed, or orifice tube plugged up, so say if the compressor grenaded and somebody didn't clean the system out. Or we could have moisture in the system causing the TXV to freeze up. And again, control valve failure in a variable displacement system. If we got a low high side and a high low side, so symptoms of or causes of this are usually a worn or failed compressor. So it can't pull as hard on the suction side, and it can't push as hard on the discharge side because it's weak. You know, it's like having blow-by in your engine. It's just tired and it won't output as much. Slipping clutch or belt is another cause of that. You could have a blockage on the high side. And in a variable displacement compressor, again, failed or blocked expansion valve, blockage between the receiver dryer and the evaporator core. So if we have a normal high side, but our low side is virtually nothing, or even in a vacuum sometimes, depending on the system. This could be that the blend door is stuck. So basically the evaporator could be icing up. Our heater blower motor isn't working. So the heater blower is very, very important because it actually heats the refrigerant up. So if it doesn't work and the AC is still running, it will quickly slug that compressor with liquid refrigerant. Our expansion valve could be stuck closed, or we could have a restriction in the high side of the system. So what you can do is you can actually look for frost on the high side line, and that's usually where the blockage would be, right where the frost stops. So your low side line will sweat, but your high side line should never sweat or be frosted. If our high side is high and our low side is normal, most common cause for this is air in the system. So if our high side is normal, but our low side is high, common causes for this is our expansion valve is just stuck. So another thing is that our capillary tube, so with our little temperature sensing bulb, may not actually be making proper contact with the evaporator, again causing the expansion valve to remain closed. So if we have equal pressures when operating something that's close to or exactly static, it's most likely an issue with the compressor clutch not like being worn out, not engaging, our wiring is broken, or we have an issue with command from our AC module to our compressor. If static compressors are at their proper level, if static pressures are at their proper level, the compressor should kick on even if the charge is lower than it should be. So our low pressure switch may also have failed in this case. So if we have normal pressures but no cooling, most likely an indication of moisture in the system. If the system was completely empty at any point and the receiver dryer wasn't replaced, this desiccant's probably completely saturated. So if we have no pressure on both gauges, system's empty, plain and simple. So if the system was charged recently and now it's completely empty, you most likely got a very large leak from either a failed hose or a failed compressor or a broken condenser or something like that. So I hope you've enjoyed this video. Like Porky Pig says, that's all, folks. I hope that you gained something from my constant babbling. I worked for many, many hours on this lecture, so if you enjoyed it, please give it a thumbs up. I really, really appreciate it. So one thing I please beg of you is please do not ask me, my AC doesn't work, what is wrong? You know, there's so many things that can go wrong. And most of the time when there is something wrong, you either get lukewarm air, warm air, or just kind of blah cooling altogether. So, you know, if you want to ask me a question of how the system works, have at her. But, you know, I kind of can't really answer the what's wrong with it. I don't know. It's just blowing hot air. Please do not discharge your refrigerant into the atmosphere. That's not good. Please do not attempt any AC repairs unless you have the proper equipment and training for this. So, thank you so much for watching. Take it easy, everyone.